Welcome to lecture number 36. So today we are going to discuss the second method of the approximation process. So this is called the variational method. So we have learned about the perturbation method or the perturbation theory. So here we are going to talk about the variational method or the variational theory. So in the perturbation method, we needed an already solved similar system or similar solution. But here, so I can write here that unlike perturbation method, we don't need an already solved similar problem. Okay, so this is one of the great advantage of the variational method. So here we can have a direct approach. So what does the variational method give us? The variational method gives us a close approximation to the ground state energy of a system. Okay, so it's also called the variational method gives an upper bound of the ground state energy. So let me write it clearly. It gives the upper bound of the ground state energy. So what is that? We will talk about right now. So let's try to give an example. So let's assume that we have a already solved system and the ground state energy. Okay, so the ground state energy of that solved system is E0. Okay. So, therefore, since it is already solved and we assume that from the Schrodinger equation we get it, so that means it follows the Schrodinger equation. So H psi naught is equal to E naught psi naught. So it actually satisfies this equation. And E naught is the ground state energy and psi naught is the ground state wave function. Means it is the lowest possible energy state for a corresponding quantum number, whatever the quantum number is. If n is equal to 1, it is 1. Okay. So now what we can do is, you see, it follows this, then or perhaps we can multiply the same equation with psi 0 star on both sides, and then it would still be the same thing. Okay. All right. And then perhaps we can integrate both left and right hand side with respect to the volume element d tau. Okay, whatever the volume element may be. So we can write that, and we can integrate with the applicable limits satisfying the system's boundary conditions. So we can write that. Now what happens is that since psi naught is okay, we can assume that psi naught is already normalized. Anyway, so since E naught is a constant term, so E naught can come out of this, right? So E naught psi naught star psi 0 star psi 0 d tau. Okay, so here if I want to find an expression for E naught right over here, so theoretically we can write that for E naught this will be equal to this is a fraction, so on the numerator we'll have integration psi naught star h psi naught d tau, and at the bottom we can have psi naught star psi naught d tau. So remember, although psi naught is normalized, and I know that psi naught star psi naught d tau integration over the full limit is going to be 1, but there is a reason that I have expressed such equation here. The reason is that suppose now we are talking about an unknown system. We don't know what is the ground state energy, but we feel that there at least exists a psi naught. Okay. Now what's the psi naught? We don't know, but we will arbitrarily guess a system and guess a function phi. So let phi be an arbitrary function. Okay. So the function that actually satisfies this equation for this system. So h phi is equal to e phi. Then we can tell. Okay. So it will give some energy. So if phi be an arbitrary function, okay, then what would happen that if we replace phi, means if we replace psi naught by phi, so we can write then the energy, corresponding energy would be E phi, okay, is equal to, we can write then, okay, so I better utilize the space over here. So we can write E phi is equal to phi star, so similarly, exactly like this, phi star phi d tau divided by phi star phi d tau. Okay. So the thing is, since this E naught is known one for a system that we know, we have assumed that E naught is the ground state energy. So we have assumed. So now there is one and only one psi naught for that. But if we find any other phi which resembles psi naught or goes very close to the psi naught, and we can find an energy expression E phi. So whatever the E phi it is, the relationship that it would carry with E naught is actually, so the relationship would be that the E phi should always be either greater or at the most equal to E naught, the ground state energy. Okay, so this is the theorem. Actually, this statement is called the variational theorem. Okay. So this is the statement, and we can say that where E naught is this expression and E phi is this expression. Okay. So the thing is, of course, now it depends on how good we can guess. Now, if we exactly guess the correct, by guessing arbitrarily, if we are lucky and somehow, although the chance is very less, but somehow if we are successful to correctly guess phi as psi naught, we will get that energy is equal to E naught, but we cannot get any energy less than E naught because there is already standardized least energy of this system. But if you are a little off from our guess, or if we are a little inaccurate from the actual psi naught, we will get some energy, but that energy has to be greater than the E naught. So that's why this statement, the variational method, gives the upper bound of the ground state energy, means it gives the energy greater than the upper side of the ground state energy. Okay, so now this variational method gives us a wonderful opportunity to choose or to find the ground state energy, or to approximately calculate the ground state energy of an unknown system. So where we do not need to have find an already satisfied or already solved system like perturbation theory. So here you see that depending on the accuracy of our guess, we would get a value very close to the E naught, and that's success. Okay, so now it depends on our method of calculation. If we are good, we can go up to 90%. If we are very good, we can go up to 95% accuracy. And if we are very, very good at guessing, then we can go up to the 99.99% accuracy, which is almost equal to the actual experimental energy. Okay, so this is all about the variational theorem and the variational method. Okay, so we will start with a very simple or a very common example. That is the example of the ground state energy of hydrogen atom, and how we can employ the variational method to guess or to approximate to predict the ground state energy of the hydrogen atom. So let's clean the board and do it. Okay, so before we begin our example on hydrogen atom, so let's make sure that the phi is called a trial function. Phi is a name. Okay, so the trial function is a very appropriate name because it's a trial and error method. Okay, so we'll guess something as a phi and we'll see how close it gets, and then if it does not work well, so we change the function and we again try, and we try it again and again and again and so on. Okay, so the question is how to guess it. So there are some systematic way to guess it, and we will do that in this in this chapter. So, but arbitrarily we can say that usually phi is taken as a function of some parameter, say like alpha, beta, gamma, etc. Where these alpha, beta, gamma, those are called the variational parameter. Okay. So the process is that, so we take the phi, we express the phi as a function of a variational parameter, and we apply the variational theorem to find out what is E phi. And once we find the E phi or whatever, once we have an equation for E phi as a function of the variational parameter alpha or beta, then we try to minimize E phi with respect to those variational parameters alpha, beta, gamma, etc. individually. Okay, and then we solve for alpha or beta or gamma, and then putting those values alpha or beta, gamma into the expression of E phi, we try to find the ultimate energy, that is E phi. So let's just follow the example, then the process would be clearer to us. Okay, so let's talk about the hydrogen atom. Okay, so for hydrogen atom we are guessing the ground state energy. Okay, so what is the condition for ground state energy? So we know for condition for ground state energy is when the electron stays n is equal to 1, and we all know that when the electron stays n is equal to 1, so therefore it implies m is equal to 0. So whenever m is equal to 0, obviously m is equal to 0. So this readily implies that these y, the spherical harmonics y00, 0, this has no role. Okay, because the hydrogen is in 1s orbital. Okay, so since spherical harmonic has no role, then the ground state energy or the corresponding psi or whatever, or better to say the corresponding Hamiltonian operator, is a function of r only. Okay, or it only involves the radial part, because we are not considering theta phi part. Okay, because the spherical harmonics has no role here when electron is in 1s, because it is ground state. Okay, so since h is a function of r only, we are going to write the Hamiltonian operator for hydrogen atom. So can you write it with me? So of course this is minus h cross square divided by 2 mu. Mu is the reduced mass of electron and proton. And then 1 over r square, okay, and then ddr, okay, of r square ddr, okay, and so we can write that minus or plus the ur, so the plus ur becomes basically minus here we have at the bottom we have 4 pi epsilon naught r, okay, and at the top we have E squared. So that is the potential energy, the electrostatic potential energy. So I guess the video has been paused here. So let's try to resume the video. Okay. Okay, so I think there is some problem. Okay, so due to some technical snag, the last time the video was paused momentarily, and it was not recording any video, but it was only recording the audio. Anyway, we are back, so we can call it a part 2. So I am not sure whether I can join the earlier video with this one. But if I'm unable to, so we will deal in this lecture as the part 2 of lecture number 36. Okay, so let's continue. So this is the Hamiltonian for the hydrogen atom, okay, where the electron is in n is equal to 1, or this is basically is in the ground state, okay. And then, so therefore, we need to guess a trial function, that means a phi. So what should be the phi? So therefore we can guess it in many ways, but remember, while guessing we have to remember those terms that can it be well behaved, or it should be well behaved, okay, and also would it be an acceptable wave function. That means we cannot just predict anything as phi. So there should be something, so should be well behaved or acceptable, etc., etc. So what should be a good guess about phi? Okay, so can we guess it as e to the power alpha r? Okay, so yeah, can we guess that? Or can we guess it as e to the power minus alpha r? Okay, or can we guess that as e to the power alpha r square, or can we guess that as e to the power minus alpha r square? Okay, so whatever you would guess, I would leave this up to you. So use your best judgment to pick a well behaved or an acceptable phi, and remember the limit of r is 0 to infinity. So keeping that in mind, you may pick any phi. So remember that if phi may not be, we may not be able to normalize the phi, so that may or may not happen, okay. So we may or may not be able to normalize it, but the limit is this. So within this limit, let's try to pick the most suitable, well-behaved or most acceptable wave function as phi, okay. So even if we do that, so what's next? Okay, so what's next is something like this. So now we have expressed our Hamiltonian H, and we have guessed our we have picked our trial function. So first we will try to find E phi. So E phi should be equal to this expression, that is e to the power something whatever we have picked, and this is a real function. Okay, so so before we begin, the variational parameter, let's be real, let alpha be real. So it doesn't matter, so phi star means phi, so phi star h phi. So we have to evaluate this integral, we have to integrate this part. Okay, so that means we have to take the Hamiltonian operator on phi and then multiply it by phi star, and then we have to integrate it from 0 to infinity, and at the bottom we have again phi star phi, means basically phi square del tau 0 to infinity. So then you have to evaluate this integral, then we have to divide this integral by this, then we will find a value of E phi. Now this E phi, okay, definitely it should be a function of alpha. Okay, so now we have to optimize E phi, that means we have to minimize E phi for some value of alpha. So therefore we have to set that the first derivative with respect to alpha. Okay, so we can take that ddE of alpha with respect to alpha, that is dd alpha of E alpha, we should set that is equal to 0 for what value of alpha. So that means if we try to solve this equation, then we will find out a value of alpha for which this is true, and we will, since we are already dealing with the ground state energy, so we will take that this is the energy minima. Okay, so then we have to take that alpha value and we have to put that alpha value over here. Once again we have to put the alpha value back here. So once we put the alpha value back here, we would be now expressing the energy in some numerical value, because we will have some sort of expression. Okay, and then let's our job would be to compare this obtained value, whatever we get calculated from calculation, with the ground state energy of the hydrogen atom, which is minus 13.6 electron volts. So with this, let us evaluate how close we go, and then we can get to know that how good was our guess. That means the trial function. Okay, so now it's your job to find it. Please do this exercise and let's try, and you please try to find out that how close you can get with this. Okay, and you can get help from your textbooks. Okay, so next we will deal with a couple of more examples on the application of variational theorem and guessing the trial function. Okay, so let's clean the board and do it. Okay, so before we proceed, we have to make ourselves familiar with the proof of the variational theorem. So whatever the variational theorem, the statement I just gave you, the statement says that E phi is greater than is equal to E naught, means the ground state energy. So this is the statement, and I have roughly explained you that what does this mean. So the little derivation that we made a little while ago is not the actual classical proof of the variational theorem though. So it could be proven in a more generalized manner. For that, I recommend you to look at the textbook for its more orthodox proof. So now let's quickly take a look at the application of variational theorem. So these are the two most common or most popular application of variational theorem you will find in most of the textbooks. So the number one is the application on the harmonic oscillator. So harmonic oscillator has this Hamiltonian operator, you can recognize it, and now it says you try the trial function phi is equal to cos lambda x, where the limit of the x is this. Okay, and the lambda is the variational parameter. So not only you have to find the energy expression, but you have to optimize the energy with respect to lambda. So now my question is, what if you find, if someone guesses the trial function as sine lambda x instead of cos lambda x? So how far this guess would be reasonable? And in that case, what would be the range of x? And what would be the end product? Okay, so you have to concentrate on that. So it's your job to find out firstly this, and secondly, can anyone take up the value of phi is equal to sine lambda x? Okay, the next one is called a quartic oscillator. So the quartic oscillator is similar to the harmonic oscillator, but here the potential energy part is dependent on x to the power 4. So here goes the Hamiltonian. This is the kinetic energy part, plus this is the potential energy part, Cx to the power 4. And then it asks you to find that, or to consider the trial function phi is equal to e to the power minus alpha x square by 2. So therefore here alpha is the variational parameter, and you have to optimize everything, the energy with respect to alpha, and you find out the ground state energy, or in other words, you have to find E phi. Okay, so the ground state energy by assuming phi is equal to this. Okay, so these are the two classical examples that are dealt in most of the textbooks. So therefore, the last part of this chapter is how to find or how to guess systematically a trial function. Okay, so we will discuss that in our next lecture. So the topic of our next lecture from this chapter would be that how to systematically guess or consider a trial function in the variational method. Okay, so you please study these part from the textbook, and I will try to join the two interrupted videos into one session. If not, I will post this as a part 1 and part 2. So let's see how I can go. So anyway, so see you in the next lecture soon, and till then, goodbye.